Okay, welcome to the class. So from today on, we'll dive into another chapter, which is about geometric and Cartesian vectors. Today, let's have a look at the first lesson of this chapter, which is about introduction to vectors. First, let's have a look at today's learning goals. So after this lesson, you are expected to be able to first understand the concept of vectors, then differentiate scalars and vectors, represent vectors in different ways, and understand concepts related to vectors such as magnitude, direction, two-bearing, quadrant-bearing, as well as parallel, equivalent, and opposite vectors. Okay, first of all, let's have a look at the concept of scalar and vector. A scalar is a quantity that describes magnitude or size only, with or without units. It does not include any direction. Whereas a vector is a quantity that has both magnitude and direction. For example, regular numbers such as 1, 3.2, -5, square root of 2 are numbers. So these numbers are scalars, right? And also, for example, -5 degrees Celsius, 72 degrees Fahrenheit are the temperatures. Temperatures usually are scalars. And areas such as 24 square meter, 15 square centimeters. These areas are also scalars. Okay, you can have a look at some other examples as well. For example, distance, speed, mass are all scalars. Whereas displacement, velocity, and force are usually vectors because for these quantities, they have both magnitude and direction. For example, 1 centimeter at angle of 30 and or 5.3 kilometers north. These displacements have both magnitude and directions. So they are called vectors, right? So you need to be able to differentiate scalars and vectors. Okay, I'll give you some time to have a look at the concept here. Okay, so note that not all physical quantities can be expressed by magnitude alone. For example, gravitational pull has magnitude, but it also has downward direction, right? A pilot needs to set both speed and direction of a flight. Police at an accident scene need to consider the momentum of cars of different masses traveling in different directions. So that's why we need to introduce the concepts of vectors. Okay, so if we are clear about the concept of scalars and vectors, then let's consider an example question here. Can you state whether each of the following is an example of vector or a scalar quantity? First, a car traveling at 50 kilometers per hour to the east. Next, a child pulling a wagon with a force of 100 Newton at 30 degrees to the horizontal. Then a man's mass of 88 kilograms. Next, a woman skiing at a speed of 25 kilometers per hour. Then a parachutist falling at 20 kilometers downward. Then acceleration due to gravity on Earth of 9.8 meters per square seconds downward. Then number 5, and last, your weight on a bathroom scale. Okay, I'll give you 3 minutes to have a look at these questions. Okay, can you state whether each of the following is an example of vector or a scalar quantity? Okay, have you finished? Okay, let's have a look at the solution together. So according to the concepts of scalar and vector, you know that first the magnitude of Okay, in question A, we know the magnitude is 50 kilometers per hour, right? And there is also a direction which is east. So this is a vector. In question B, the magnitude is 100 Newton and the direction is 30 degrees to the horizontal. So this is also a vector. In question C, the magnitude is 88 kilograms, but there is no direction. So this is a scalar. In question D, the magnitude is 25 kilometers per hour, but no direction is given. So this is a scalar. Remember, we have talked about the difference between speed and velocity, right? Usually a speed is a scalar, whereas velocity is a vector. Question E, the magnitude is 20 kilometers per hour and the direction is downward. So this is a vector. F, the magnitude is 9.8 meters per second. And the direction is downward. So this is a vector again. Question G, the number 5 has magnitude only. So it is a scalar. It does not matter that it has no units. H, a scale uses downward acceleration of gravity to calculate your weight. So weight on the scale is a vector. Weight is sometimes used as a synonym for force. Your weight in newtons is your mass in kilograms multiplied by the acceleration due to gravity, which is 9.8 meters per square second downward on Earth. Although your mass remains constant, your weight would be different on another planet because gravity is different on the other planet. Okay, do you have any questions? No? Okay. Then let's have a look at the representation of vectors. How we can represent vectors. A vector can be represented in several ways. In words, for example, as 5 kilometers at an angle of 30 to the horizontal. So you can express a vector in plain English words, right? Second, you can also express a vector using a diagram as a geometric vector, which is a representation of a vector using an arrow diagram or directed line segment that shows both magnitude or size and direction. The length of the arrow represents and is proportional to the vector's magnitude. For example, in the first example, 5 kilometers at an angle of 30 to the horizontal can be represented using a directional arrow like this. A directional line segment or a line with an arrow like this, right? You can also represent a vector using symbols. For example, using the endpoints of the arrow, vector AB. Point A is the starting point or initial point, which is also known as a tail, right? And point B is the end or terminal point of the vector, also known as the tip or head. Okay, you can also use a symbol like the vector of V like this. Just put a letter V and a directional line section on top of the letter, such as vector V, vector U, vector A, B, C, and so on. So there are several ways we can represent a vector, right? Okay, next, let's have a look at the magnitude and direction of a geometric vector. The magnitude or size of a vector is designated using absolute value brackets. The magnitude of a vector AB or vector V is written as the absolute value brackets of vector AB or the absolute value brackets of vector V, like this. Are you clear? So these two symbols means the magnitude of the vector only, does not contain any direction. On the other hand, a vector's direction can be expressed using several different methods. In the diagram of vector AB, it is expressed as an angle moving counterclockwise with respect to a horizontal line, which is shown on the bottom left. In navigation, vector directions are expressed as bearings. So there are two types of bearings, which we'll have a look at in the next lecture slides. One of them is called true bearing, and the other one is called quadrant bearing. So simply speaking, there are three ways we can express a vector's direction geometrically, either using an angle moving counterclockwise with respect to a horizontal line, or use a true bearing, or use quadrant bearing. So next, let's have a look at the differences between true bearing and quadrant bearing, okay? First, a true bearing or a azimuth bearing is a compass measurement where the angle is measured from the north in a counterclockwise direction. True bearings are expressed as three-digit numbers, including leading zeros. Thus, north is a bearing of 0, 0, 0 degree. East is 0, 9, 0 degree. And south is 108 degrees. And west is 270 degrees. For example, a bearing of 040 degrees is an angle of 40 degrees in a clockwise direction from due north. For simplicity, we'll use the word bearing to refer to a true bearing. Okay, so when you see the word bearing, by default, that means a true bearing. You understand? Okay, next, there's another type of bearing, which is called quadrant bearing. Directions can also be expressed using a quadrant bearing, which is a measurement between 0 and 90 degrees east or west of the north-south line. The quadrant bearing N 23 degrees W is shown in the diagram. That means north 23 degrees west. A quadrant bearing always has three components. The direction it is measured from. So in this case, N is the direction that is measured from, right? The angle, in this case, angle is 23 degrees. And then the direction toward which it is measured. So in this case, it is west. The quadrant bearing N 23 degree west is read as 20 degrees west of north, whereas S 20 degrees E is read as 20 degrees east of south. All quadrant bearings are referenced from north or south, not from west or east. Are you clear? Okay, I'll give you 5 minutes to have a look at the concept of true bearings and quadrant bearings, okay? Careful with the differences between the two types of bearings. Okay, if we are clear about the concepts here, let's do a practice example. Describe each vector in words. Okay, there are 3 vectors in the diagrams, right? Can you describe them in words? I'll give you 1 minute to have a look at this question. Okay, let's have a look at the solution. So in question 8, the vector is 14 centimeters at 110 degrees to the horizontal. So remember that there are 3 methods we can express a vector, right? So apparently we are using the first method here to denote its direction, the degree between the vector and the horizontal. And in question B, this vector can be expressed as 2.3 kilometers. That's the magnitude, right? 2.3 kilometers at a true bearing of 135 degrees. Or you can also say 2.3 kilometers at a bearing of 135 degrees. Remember, when you don't say true bearing, the bearing by default means true bearing, okay? And the vector in question C can be expressed as 9.8 Newton at a quadrant bearing of of 35 degrees west of south, or S 35 degrees W. Any questions? Okay, then let's consider another example. Draw a bearing. Draw a geometric vector with each bearing. Show the scale that you used on each diagram. Okay, I'll give you 4 minutes, 1 for each, to have a look at this example, okay? Try to solve this by yourself, and then we'll have a look at the solution together. All right, if you have finished, let's have a look at the solution. So remember to state the scale you use when you draw each vector, okay? Okay, so let's have a look at the solution for each of the questions. In question A, the vector can be drawn like this. So the scale is 1 centimeter is 1 kilometer. And then in question B, the vector is like this. So note that the true bearing of this vector is 295 degrees. And it measures from the true north clockwise for a degree of 295. And the scale is also 1 centimeter to 1 kilometer. And in question C, the vector looks like this, which has a quadrant bearing 40 degrees east of north. And the scale is 1 centimeter to 10 kilometers per hour. And in question D, the vector looks like this, which has a quadrant bearing 70 degrees west of south. And the scale is 1 centimeter to 10 kilometers per hour. Okay, any questions? All right, no questions. Let's have a look at another example. Convert between true bearings and quadrant bearings. Question 8, write the true bearing 150 degrees as a quadrant bearing. And in question B, write the quadrant bearing 50 degrees west of north as a true bearing. Okay, I'll give you 5 minutes to have a look at this question. Okay, have you finished? Okay, let's have a look at the solution. So in question 1, note that 180 degree minus 150 degrees is 30 degrees, right? So a true bearing or a bearing of 150 degrees is equivalent to a quadrant bearing of 30 degrees east of south. In question B, note that 360 degrees minus 50 degrees equals 310 degrees, right? So a quadrant bearing of 50 degrees west of north is equivalent to a true bearing of 310 degrees. Okay, any questions here? Okay, I'll give you some time to have a look at the solution here. Any questions, just let me know, okay? So be sure that you are able to convert between a two bearing and a quadrant bearing. All right, if no questions, let's have a look at another concept, which is called the parallel vectors. Parallel vectors have the same or opposite direction, but not necessarily the same magnitude. So for example, in the trapezoid below, trapezoid PQRS, it is shown that line segment PQ is parallel to SR, right? So we know the vector PQ is parallel to vector SRS. Also, we have the vector PQ is parallel to vector SR. Note that parallel vectors can have same or opposite directions. This concept is pretty straightforward, right? Do you have any questions? No? Okay, so basically this concept shows the parallel vectors geometrically. All right, then let's have a look at another related concept, which is called equivalent and opposite vectors. Equivalent vectors have the same magnitude and the same direction. The location of the vector does not matter. So as long as two vectors have the same magnitude and the same direction, they can be called equivalent vectors. Well, opposite vectors have the same magnitude, but opposite direction. Again, the location of the vectors does not matter. The opposite of a vector AB is written as negative vector AB. So, for example, if we have a parallelogram like this, consider the parallelogram ABCD as shown here. The table on the right shows the pairs of equivalent and opposite vectors. So for example, we know that vector AB and BC are equivalent, right? So if they are equivalent, we can write vector AB is equivalent. Use the equality symbol, right? So if the equality symbol joins two vectors, that means that two vectors are equivalent, which means they have the same magnitude and same direction. Also, we have vector BA is equivalent with vector CB. Vector AB and the vector BC are equivalent. Vector DA and vector CB are also equivalent, right? Similarly, according to the concept of opposite vectors, we have vector AB and CD are opposite. Vector BA and BC are opposite. Vector AD and CB are opposite. And vectors ADA and BC are also opposite. So now are you clear with the concept of equivalent vectors and opposite vectors? Are we clear? Do you have any questions? Okay, so next let's have a look at example to check your understanding for this concept. Question A, draw a vector equivalent to vector AB labeled EF. Can you do that? Question B, write an expression to show how vector AB and EF are related. C, draw a vector opposite to vector AB labeled vector GH. Then write an expression to show how vector AB and GH are related. Okay, I'll give you 5 minutes to consider this example by yourself. Okay. Okay, let's have a look at the solution. So first of all, if we want to draw a vector equivalent to vector AB, remember that equivalent vectors have the same magnitude, right? And same direction, but position does not matter. So we can draw a vector like this. This vector has the same magnitude and direction with AB. And remember the position of this vector does not matter, right? So this vector is called EF. Then we know vector AB and EF are equivalent, so we can use a symbol like this to indicate these two vectors are equivalent. Remember that? And in order to draw an opposite vector, remember that opposite vectors have the same magnitude, but they have the opposite direction, right? So we need to draw the arrow like this. So this is called GH. GH is opposite to vector AB. And we can use this symbol to indicate they are opposite. Vector AB equals negative vector GH. Understand? Okay, do you have any questions? All right, if you don't have any questions, let's make okay, this is a proper writing of the solution of the previous example. Okay, if you like, you can take a note of this. Okay, so let's make a summary of today's lesson. So today is the first lesson of this chapter, which introduces the basic concepts related to vectors, scalars, and how we can represent vectors in different ways. Remember, we have mentioned 4 ways to represent the vector, right? Then you need to be able to understand the trivial concepts related to vectors, such as magnitude, direction, true varying, quadrant varying, as well as parallel, equivalent, and opposite vectors. And remember that you should be also able to convert between the true varying and quadrant varying, right? Okay, so if you don't have any questions, remember to complete today's homework and submit them before the deadline onto Google Classroom, okay? Okay, so that's all for today's lesson. Again, remember to complete your homework.